Hi, I'm David, and this is a revision seminar for Maths 1M. Now you've seen my face, I can turn the camera back off. Okay, this revision seminar is about the section in the course called Parametric Curves. But really, to say parametric is a bit of a misnomer. All curves are parametric, but they don't have to be represented parametrically, and so I'm just going to call it curves. So curves are a specific kind of object, and you've been looking at curves in 2D, but you can make them in 3D just as easily. And when you're understanding any mathematical object, there are several questions you should ask yourself. You should ask, what is it? Which means, what's the definition? What does it mean? What are the ways of representing it? How do I convert between those representations? And then you should ask yourself what you can do to it. So what sorts of things can you say about it? What properties does it have? What sorts of things can you calculate from it? What things belong to it? How do we connect, join them together to make new ones? That sort of question. And then you can ask yourself, what do we do with it? Which means, what are they useful for? And how does it connect to basically everything else? So either making new math stuff or solving non-math sorts of problems with them. So I'm only going to look at the first two with curves, though I will say that curves, in terms of what they're useful for, outside maths, they're about tracking how an object moves can be done with a curve. And also it just allows us to be able to describe things that are basically straight or curved lines in space, which is a useful thing to be able to do. Anyway, what are curves? The easiest way to get a handle on what curves are is to draw a picture of them. So, here we go. Picture something like that, or something like that. It could join up to itself, or it could be straight. Curves, in a way, are pictures that can be drawn with a pencil or a pen without lifting your pen off the page. Technically, you could be allowed to lift your pen off the page, but most of them are like this. So to a mathematician, a circle is a curve, a straight line is a curve. That one's not particularly straight, but it's supposed to be. Just because curve is not referring to the fact that it is curved, it's just a useful word that we've appropriated from ordinary English to describe something that you can draw like this. Now, you don't necessarily have to draw it on a piece of paper. It could be in space. You could have a curve that moves like that. But that's what a curve is. Now, that's of course not a mathematical definition, but I don't think we need one at the moment. Okay, I'm now going to ask myself, how can you represent these things? Because when mathematicians actually define what a curve is, it's actually a particular representation of curve. So obviously you can represent them by drawing them, but you can also represent them as sort of a mathematical imagining of what that drawing process is. So basically, when you draw a curve, you are following a point as it moves. Okay, the pencil point is your point, and it moves along the paper, and you follow that as it moves, and it leaves a track on the paper, which is the curve. So I'm just going to write that bit down. As it moves. That's a curve. And that's the idea of this parametric that they're talking to. We can have a parameter which is a fancy word for variable. It's normally called t, or it could be x or theta or whatever you want it to be. It's usually t, but it doesn't have to be. You can have a parameter t that tells you where the point is up to at the moment as you follow it along its track. Okay, so I like to think of this as a particular view of function. There is the parameter t, which lives on a line somewhere. It's just a number, and often it's between 0 and 1. And then as the t moves along, your curve is traced out. So this point 0 would correspond to a particular point here, and then as this moves along here, the curve will trace itself out until you get to here, which corresponds to the point 1. And the points somewhere in the middle correspond to points somewhere in the middle of your curve. So this point, for example, may belong there, this point may belong there, and so on. And so you could imagine if t does go from 0 to 1, that's the percentage of the curve that you've covered. The problem with that is, of course, that it doesn't necessarily have to represent an actual percentage. When t is up to 0.5, it doesn't mean you've covered half of the length of the curve, because different parts of the curve might go faster than other parts of the curve. So, for example, if this point here corresponds to that, I've got a long way to go in this short amount of t, so this second part of the curve goes faster than the first part. But all the same, your t can tell you where you're up to. Every point, every number t corresponds to one of the points on the curve. And as the t goes up, the point moves along the curve, and together, all of those points are the points on the curve. Okay, so in a way, this parameterization, they call it, this way of describing a curve parametrically, is a way of listing what all the points on the curve are. So I'm just going to write that down on a new page. Describing the curve parametrically is saying how to write all the points on the curve. So, for example, it might be something like cos t sin t for t between 0 and 2 pi. Okay? And what this does is it tells you how to make points which are on the curve. Just pick a value of t, sub it in, and you have a point on the curve. And I could choose any number of numbers between here and here, and that would make more points on the curve. It describes all the points on the curve, each individually. Okay. However, there is another way of representing a parametric, well, representing a curve. Okay? We have a description of what all the points are individually. We also have our graph, of course. There's a third way of describing the curve. Any set of points x, y ought to, now I say ought to, it's not necessarily true what I'm about to say, but in general it is, ought to have an equation to tell if a point is in the set. So my parameterization tells me what each point on the curve looks like, what its coordinates are, and I can name points on the curve and I can give their coordinates until the cows come home by just continuing to choose new values of t or x or theta or whatever the parameter is. However, on the other hand, if I gave you a random point and said, is this point on the curve, that's a whole different question. And you would have to try and write it in the format of the parameterization in order to tell. Well, there's an alternative description of a curve, or indeed any set of points, which is you might have an equation which, if you sub the formulas, the coordinates in, it will tell you whether it's on the curve or not. And best way is to do it with an example. So, for example, the set of points x, y such that x squared plus y squared is equal to 1. Is the point 1, 3 in this set? Well, I can tell because all the points in the set, their coordinates satisfy this equation. So let's see, 1 squared plus 3 squared is 10, which is not 1, so no. This point is not in the set. Is the point 1, 0 in the set? In this set, 1 squared plus 0 squared equals 1, which is indeed 1, yes, it is in the set. And you could imagine getting every possible point and subbing it into that equation and eventually figuring out what the curve looks like. So far we have subbed in the point 1, 3, 1, 1, 2, 3, and it wasn't in the set. And we've subbed in the point 0, 1, 1, 0, which is here, and that is in the set. We could sub in the point -1, 1, and that's not in the set. And we could sub in the point 0, 1. We could sub in the point 1 on root 2, 1 on root 2. We could sub in the point -1 on root 2, 1 on root 2. We could sub in 0, -1, and we could sub in, I don't know, 2, 2, which is not in the set, and 0, 0, which is not in the set. We could sub in any number of points, infinitely many, and eventually be able to discover all the points that are on the set. And my set turns out to be a circle. It's not a very efficient way of finding what a set is, but essentially that's what the equation's doing. So now we have these three different ways of representing a curve. We have the graph, where you just draw what all the points are. We have the parameterization, the parametric form, which is a description of what the coordinates of the points on the curve are and how to calculate them given a value of t or theta or x. And we have an equation which is a rule for telling whether a point is on the curve or not. All right, well, if you're going to have any different representations of things, you need to have ways of converting between them. Before I do that, I've just realised that we've seen this before. I mean, any time when you're trying to understand a concept, you should really try and connect it to other things that you know. So, we've seen things in Maths 1M that have parametric form, and also have this form here with the equation. This is called Cartesian form, just by the way. Okay, they also have an equation, which is called Cartesian form. You've seen that before when you did lines, when you were doing vectors. So I'm just going to put that in now, because connections between things is really what learning is. And at university in particular, they're not really expecting you to just be able to do a particular procedure in a particular situation. They're going to put you in situations that are similar, but and sometimes not at all like things you've done before, and you're going to need to connect the information together. So making those connections is really a key part of learning ever, but especially in university. So let's just another example for ourselves. We have lines. Okay, so a line, for example, might have an equation like this. X plus y minus 3 is equal to 0, and that's the Cartesian form. And that could be written in any number of different ways, x plus y equals 0, y equals minus x plus 3, various different formats. And there's a parametric form as well. Now you might not see this as parametric form. Your head probably says, but David, that's vector form. But really, parametric form in a way is just a description of what the points on the curve are like. And so this straight line, the points on this curve are completely described by that equation there. Normally when you write parametric form, you write them as two coordinates, you could just as easily say, well, this is minus tt and 3 minus t if you wanted to, but there's no particular reason why you can't leave it like this for your own purposes. For the purposes of the person marking your exam, I'd write it with the two coordinates lumped together like that, because that's what their solutions will look like. And people who find their students' solutions match their own solutions, I find it easier to mark their stuff and are therefore happier, and happier markers are more generous. Of course, if you do write something that is mathematically correct but not what they are expecting, you'll usually get the marks. But in general, you should err on the side of caution and make it look like what they want. I should say t is in R. You're supposed to specify what the t is. Okay, you've seen that before, and you have methods of converting between those when you're looking at straight lines. And we're going to try and abstract from those methods and just generally find ways of converting between the different representations. So I'm going to write that down. Converting between forms. And it might be easier, instead of just giving you a method, because that's often really difficult to describe, just to give you a few examples and try and draw out the commonalities between them. So I'm going to go from parametric to Cartesian. So let's see, curve. Let's have t plus 1 t squared for t in R. So that's my curve, and I'm going to convert to Cartesian form. Find a Cartesian equation. Okay, what I'm going to do first is try and understand what sort of a curve this thing is. Now, this is not wholly necessary to solve this problem, but I'm going to feel better if I know what that looks like. And so, because I feel better, I'll be more able to solve the problem. So that's what I'm going to do. I'm going to see if I can find points on this curve. And it's also going to illustrate to you, and to myself, that this really is a description of what the points on the curve look like. Okay. All right, when t is equal to 0, I get 0 plus 1, 0 squared, which is 1, 0. And that's this point just here. T equals 0. All right, when t is equal to 1, I get 1 plus 1, 1 squared, which is 2, 1, which is just here. When t is equal to 2, I get 2 plus 1, 2 squared, which is 3, 4. 3, 1, 2, 3, 4. That's t equals 2. Okay. All right. I could do t as a half or t as 1.5 to try and fill in a few more. I'm going to actually go into the negatives to see what I get there. T equals minus 1 is minus 1 plus 1 minus 1 squared, which is 0, 1. Okay, that's here. And t is minus 2 is minus 2 plus 1 minus 2 squared, which is minus 1, 4, which is there. Okay, and so as the t moves from minus 2 to plus 2, it has to pass through all of those points, and so it's going to come down and do something like this. So it looks like my curve is a parabola. Okay, so I have an expectation of an equation that a parabola might satisfy, something like y equals something squared. That should do the trick. So that's what I'm hoping for, and drawing it made that connection in my mind. It made this expectation of what I think the equation ought to look like. Okay, but even if I hadn't drawn that, I could have made a pretty good guess at how to create this equation. Okay, so what I'm going to do is I'm going to take from this that this is the x coordinate here and this is the y coordinate. I'm going to write that down. X is equal to t plus 1 and y is equal to t squared. And I need to somehow find from that information about a single equation involving both x and y, or maybe just one of them, a single equation involving x and or y, but not involving t, that will allow me to check whether a point is on the curve or not. It's not supposed to involve t because it's not supposed to tell me what the points on the curve are. It's supposed to check to see if they are, to see if a point is on there. So the quickest way is probably to get t equals and then sub that into the other one. That looks like it's going to be a productive method today. So I'm going to get from here that x minus 1 is equal to t, and then I'm going to sub that into the other one. Sub into y equals t squared, so I'll get y equals x minus 1 squared, and there's my Cartesian equation. Is y equals x minus 1 squared. Okay, I'm just going to check that. It should have the property that if I sub points that are on the curve into there, then they will come out as correct. And if I sub points that aren't on the curve into there, then they won't come out as correct. So let's see, check. Okay, so 1, 0. So let's see. I'll sub it into the right, this expression just here on the right-hand part of the equation. So let's see, 1 minus 1 squared is 0, and that is what it's supposed to be. That's the correct y-coordinate, so yes, okay. And let's try 2, 1. 2 minus 1 squared is 1 squared, which is 1, which is the correct y-coordinate. Excellent, so that point works as well. And let's see, let's pick a point that isn't on the curve. How about 0, 0? So when I sub that in, it shouldn't work. So 0, 0. So 0 minus 1 squared is 1, which is not the correct y-coordinate, so no, that point isn't on the curve. Okay, it's working the way it should. I've only tested 3 points, but that should be enough for me to feel better. Points that are on the curve seem to be making the equation true, and points that are off the curve seem to be making the equation not true. So it seems okay. Excellent. Let's try another one. My curve is going to be 2 cos theta, 3 sine theta, for theta between 0 and 2 pi. Okay. So that's a parametric form. I've got a parameter, it's called theta today instead of t. And that parametric form describes what all the points on my curve look like. So let me do some drawing and see if I can figure out what this curve looks like. I've got to guess that because it's involving cos and sine, and the circle involves cos and sine, that it's going to be sort of circular-ish. And let's give it a go. Okay, so I'll try theta equals 0. So I'll get 2 cos 0, keep drawing a theta, 0, 3 sine 0. Now cos of 0 is 1 and sine of 0 is 0, so I get 2, 0, which is here. That's theta equals 0. Theta equals pi on 2. I'm just picking angles that I know the answer to. And so a good ones to pick is the multiples of pi on 2, because you know that cos and sine have easy answers for those, and it'll make it easier to figure out. So I get 2 cos pi on 2, 3 sine pi on 2. Now cos pi on 2 is 0 and sine pi on 2 is 1. Okay. 1, 2, 3. That's theta equals pi on 2. Now I won't write the rest of them, I'm just going to imagine them. So when theta is equal to pi, theta, where are we? Pi on 2, theta is equal to pi, 2 cos pi is minus 1, so we'll get minus 2, sine pi is 0, so we're going to get minus 2, 0, which is here. Theta is 3 pi on 2, cos 3 pi on 2 is 0, sine 3 pi on 2 is minus 1, so we're going to get 0 minus 3. 2 pi, cos 2 pi is 1, so we get a 2, 3, sine 2 pi is 0, so that'll give us back to the beginning again. Okay, so my curve links up to where it started. That's great. And I'm presuming it's going to fill in the gaps in between them in some way. Let me just try another one. Let me try theta's pi on 4, like halfway between these two. 2 cos pi on 4, 3 sine pi on 4. Okay, so that's 2 on root 2, 3 on root 2. Root 2 is about just under 1.5. So 1 on root 2 is about 0.7, I think. So this is about 2 on root 2, it's about 0.4, 1.4. So 1.4 and 3 times 0.7 would be about 2.1, so it's about here. Okay, so that's pretty good. This is going to, I reckon, go like that. Now, none of that was technically necessary in order to convert this to Cartesian form, but I feel better because it is in fact an ellipse the way I thought it might be. Okay, and it does look like actually it moves at different speeds. It's going to move faster here than it does here because it took me pi on 4 to get there and pi on 4 to get there. So it's not moving at the same speed all the way around the oval, but it does come back to the beginning. Sweet. Okay, so I now need to try and create this Cartesian equation. So I need to make an equation that doesn't involve theta because I'm not allowed to know what points are on the curve. I'm just got to check whether they're on the curve or not. And the usual way we start with that is to say x equals and y equals. So if x, y is on the curve, then x is 2 cos theta and y is 3 sine theta. Actually, I'm just going to go back and fill that in there. That's probably a good place to start your working, otherwise it just seems weird to start there. So if x, y is on curve, right. It's telling a good story there. So I want to create an equation that x and y satisfy when the point x, y is on the curve. So I'll start with if x, y is on the curve, then blah, blah, blah. Okay, so let's see. Well, I suppose. I could do this. X on 2 is cos theta and cos the minus 1x on 2 is theta. And then sub that into the other one and we'll get y is 3 sine of... which is, I suppose, a perfectly good equation, but it's, I don't know, it doesn't feel right. Most mathematicians do not like to have inverse functions nested into each other like that. And actually there's a good instinct which goes that actually any trig functions with their inverses inside each other, even if they're not the same one, should be able to be rearranged in some way to get something that does not involve trig functions. So the cos and the cos inverse and the sine should in some way cancel each other out in inverted commas to produce something. It's not going to just cancel each other out straight up and produce x minus 2, but it's going to be something. So there must be a better way than this. Okay. So maybe there's some other equation I know involving cos and sine that already cos and sine satisfy that equation. Actually, no, I'm being quite, that's pretty stupid what I'm saying there. Of course there is. It's cos squared plus sine squared equals 1. That's our classic trig, what's the correct word? The fundamental trig identity. So cos theta squared plus sine theta squared is 1. We know that. That's always true for any theta. So if we can figure out what cos theta is in terms of x and or y, and what sine theta is in terms of x and or y, then we can use this formula. So let's see. Well, x on 2 is cos theta, and y on 3 is sine theta. So we can sub them in, to get x on 2 squared plus y on 3 squared is 1. Now I could expand those brackets and leave it as x squared on 4 and y squared on 9 equals 1, and possibly multiply everything out and get something that doesn't have fractions on the bottom. I'm not going to do that, and that's because, well, I teach the Maths 1Bs as well, and the Maths 1Bs, that equation's a really useful way of writing it, because the 2 and the 3 specify how wide it is in the 2 direction and how wide it is in the x direction and how wide it is in the y direction. So I'm going to leave it like that, and that's perfectly acceptable. Let me just check a couple of the points to see if it's working the way it should. So the point 2, 0 is definitely on the curve. 2 divided by 2 squared plus 0 divided by 3 squared is in fact 1 squared plus 0 squared, which is 1 as it should be. Excellent, that's working out the way it should. Let me pick a point that's not on the curve. Let's see. Well, 2, 3 isn't, because it's over here in the corner of the box. Let me try that one. 2, 3. 2 on 2 squared plus 3 on 3 squared is 1 squared plus 1 squared, which is 2, which is not 1. Excellent. That point isn't on the curve, and it shouldn't, and it doesn't satisfy the equation. So this is doing roughly what I expect it to do. Excellent. Okay, so we've done some converting from parametric form to Cartesian form. It would be really nice if we knew how to convert the other way. I'm not 100% sure you've actually been asked to convert the other way in Maths 1M, except you have done it when you've done when you were doing lines, right? You have a line which has a triple equation in 3D, and you've converted that to a parametric form. So presumably the same sort of approach should work for converting any curve to parametric form. So we'll have a go at that, I reckon. But before we get to that, there's a really, really easy way if your equation is set up the way you know, in the way that's very easy. So let's have a look. E.g. All right, I'm going to convert from Cartesian to parametric. Let's see. Well, if your Cartesian equation is an ordinary function equation, like y equals something, then is a really straightforward way of turning it into parametric version. So if you've got an equation y equals x cubed, then the points on the curve all have an x coordinate. Right? And if the x coordinate is x, when I sub that into that equation, the y coordinate comes out to be x cubed. And that'll work no matter what x is. And so now we have a parametric version. I'm using x instead of t, but no one said you had to use t. It's just a letter. You can use whatever letter you want. That is a parametric form. Brilliant. I guess it would work just as well if you had x equals something with a y squared. You could just have y and then the x coordinate would be something. That's a perfectly good parametric version of the curve. Great. You can call it t if you prefer. It might make some of your other calculations, like the tangents and stuff, a little easier. But this will do. Okay, so there's that. And I could totally imagine a lecturer asking you to do that. It's not a great leap, or at least in their minds, from that to get a parametric form. But you've seen it now. Not that I can guarantee that. I don't know what's in the exam. They don't tell me that. I'm not part of the School of Maths. I don't write the exam. I don't write the solutions. I don't mark the exam. No one shows me the exam. I usually only find out what's in it the next semester that course is taught and the students bring me the past exam. So I can't guarantee that. But it's good practice as a student to imagine, well, is this the sort of thing that a lecturer could reasonably ask? How far is it, and how much connecting together of information do I have to do to make this happen? And this, well, not that much. You know, the whole point of parametric form is to describe what all the points on the curve look like, and I can do that with an equation like this. Okay, let's do another one. So here is a line equation, 2x plus y minus 2 equals 0. It's a line in 2D. And I'd like to convert that into parametric form, which means I need a description of what all the points on the line look like. There are multiple ways of doing that. I mean, my option 1 would be to do what I just did and rearrange it to get y equals. So option 1, 2x plus y minus 2 is 0. So y would be, okay, so we'll take a 2x and add a 2. And so now it looks like that. And so the points on the curve are x, and then the y coordinate is minus 2x plus 2. Okay, so that's a perfectly good parameterization. You could use t instead of x at this point if you wanted to. That's great. That's a version of it. Okay, I'm going to do option 2 as well, because you've seen something like this when you did parameterization of lines in 3D. Okay, you created parametric versions of that. And in 3D it was a triple equation, and each part involved just one of the variables. So you had like x on 2 equals y minus 1 equals z, something like that. And you said, well, if they're all equal to each other, then there must be another number that's equal to all three of them, and we'll call that number t. So that's what we're going to do. We can do that just as easily in 2D, right? So I'm just going to give that a go. Okay, so what if I rearrange it as like 2x is equal to, so we'll take the y and we'll add the 2, so 2x is 2 minus y. So now on this side I have something that's involving only x, and this side I have something that's involving only y. I've separated the x and the y, and so the number 2x is a number, and every time we calculate the number 2x it comes out to the same answer as the number 2 minus y. And so like they're equal to each other, so if I just give a name to whatever answer they're both equal to, that can be my parameter. So 2x is a number, 2 minus y is a number, they're the same number, and I'm going to call that number t so that I can talk about it. So let t be equal to 2x and simultaneously 2 minus y. Because 2x and 2 minus y, those two numbers are the same number, and I'll call that number t. And then I can rearrange that to figure out what the x-coordinate and the y-coordinate are in terms of t. So let's see, we've got t on 2 equals x. So the x-coordinate is t divided by 2. And if I add y to both sides, that'll move the y over here. And subtract t from two sides, both sides, I'll get that. So y is 2 minus t. Excellent. So I've got a description of what the x-coordinate and the y-coordinate are. So the points are t on 2, that's the x-coordinate, and 2 minus t, that's the y-coordinate. And presumably I should be able to use every possible value of t. Let's just think about it. If I think about the x-coordinates go here, I can use any x-coordinate, and that will be able to produce any t as well. Excellent. So that's another way of creating a parametric form, and we can do it with straight lines. I wonder if we can do it with other things. Like, what if it wasn't a straight line, it was some other like random thing? And what if it couldn't be rearranged to get y equals? So we've already got this idea that if we can rearrange it to get y equals, we can make a parametric form out of it. What if I couldn't? Well, as long as I could rearrange it to get the x's on one side and the y's on the other side, I could do this trick, right? That's really cool. I could do that trick. So let me just see if I can come up with an example that goes like that. Okay. Um, you guys have done logs and exponentials, right? All right, let's do that one. E to the x plus, now I don't want it to have just a plain y, even just a 2y would be able to be rearranged, so maybe y. All right, let's try that one and convert that to parametric form. Okay, so I could rearrange it to get e to the x equals y squared minus 1. Oh, sorry, minus y squared minus 1. Crap, that's completely wrong. I'm going to need to subtract y squared from both of these things, so 1 minus, right, that's better. And then we've got something involving only x and something involving only y. The number e to the x is the same number as the number 1 minus y squared. So I'm going to give a name to that number. I'm going to call it t. Let t be equal to e to the x, and t is simultaneously equal to 1 minus y squared, and we can rearrange it to get a value for x, figure out what x is in terms of t. So if we did ln on both sides, we'd get ln t equals x, and we add y squared to both sides to get it over here, and subtract t from both of these. All right, and so y would be plus or minus. Oh, that's a bit disappointing. The plus or minus isn't really nice. That's not a really nice way of doing this, is it? All right, I'm just going to have to consider them separately, and it looks like this curve, in inverted commas, is actually two different curves, sadly. Okay, so it looks like my x, y is ln t root 1 minus t, because that's the x-coordinate and the y-coordinate, or ln t minus root 1 minus t. And so I've got two different curves. But that's okay. I mean, this was just an experiment to see if I could conceivably actually do this. Like if it was conceivably possible to create a parametric form in this way. And it is. I'm feeling really good. I suppose I'm supposed to say what values t can possibly have. Well, let me look at what I'm allowed to do here. T, ln t is only defined when t is positive, so t has to be greater than 0. And root 1 minus t, that's not going to be defined if t is more than 1, because I'll get a negative number, so t is going to have to be between 0 and 1. Okay, all right. So for t between 0 and 1, I am allowed to put 1 in there because I'll just get 0 for y. Okay, so we can say since ln t needs t greater than 0 and root 1 minus t needs t less than or equal to 1. I suppose we could have gotten them back to here as well. If t is e to the x, no matter what x is, t has to be positive. And if t is 1 minus y squared, no matter what y is, y squared is positive. And so it will be less than or equal to 1 because we're subtracting it. So that's another way of getting to that, and that's probably more reasonable. Interesting. I can probably say with quite safe certainty that this sort of thing isn't going to come up in the exam unless they really carefully step you through it. They might introduce this as a new concept in the exam and do it. Not that they have any clue what's happening in the exam, but it's the sort of thing that one could do. Or you could imagine it as an assignment question, but we've of course done all the assignments by this stage. But if you're looking at this video in the future, you know, it's 2017 and you're using it to study in the middle of your course, then maybe it might come up in the assignments later. Who knows? Okay, so I think we've really done a good job there of looking at the representations of curves. They can be sets of points in essence, and you can describe what each of the points is using a parameter, and that's the parametric form. Or you can have an equation that tells you whether a specific point is on the curve or not. If you sub it into the equation, it works or it doesn't work. and that tells you whether it's on the curve or not. So I think we're good with that. So I really want to have a look and think about what else is in this section on curves, so that we can be kind of comprehensive. If you were studying for your exam, you'd do that too, right? You'd look through your notes and you'd try and make sure you didn't miss anything. Let's have a look. Okay, there's a specific kind of curve. So usually when you're doing new objects in maths, you won't, when you ask what is it, you won't just ask what the definition is and stuff. You'll also ask yourself if you've got any specific examples of them. Now we've done a few, we've seen a couple, we've seen ovals and functions, and they're kinds of curves. But there's a specific kind that was mentioned in your notes, and it's a Bezier curve. Okay. So your specific kind of curve is a Bezier curve. All right, I'd never heard of Bezier curves until Maths 1M started doing them last year. Well, I sort of heard of them, but never really known the details. And so here are the details. And what I'm going to do is I'm going to line them up in a different way than they are in your notes, so that it's easier to see the pattern that's going on. Because sometimes the pattern is easier to discern if you line them up one after the other. And that's what we want to do here. With this sort of thing, we need to know the pattern. Hello. Okay. So your Bezier curve has a beginning point and an end point, and then there's some other points in the middle which it sort of goes towards, and it just tells you where the curve is, but the curve doesn't necessarily pass through those. So beginning P0, and there's an end point Pn, because there's an n, and then there's other points it doesn't go through, but are used to define the curve. P1 up to Pn minus 1. Okay, and those are all, as far as I'm aware, they're called the control points. Okay, and there's this pattern for how you use the coordinates of those points to describe the points on your Bezier curve. You know it has to go through the point P0 and it has to go through the point Pn, and it sort of goes towards the other points as it goes along. So the points on the curve are... Okay, so suppose I've got P0 and P1, then I will use those points to construct my Bezier curve. So I'll have P0 and I'll have P1 and I'll have T of P0 and 1 minus T of P1. Okay, so when t is 0, I'm supposed to get the beginning of the curve, and when t is 1, I'm supposed to get the end of the curve, and the various days of t in between. So like the percentage of the curve you've covered. It won't really be. 50% will not be necessarily halfway along, because it might go at different speeds in different places. Let me see, when t is 0... Oh crap, I've got it round the wrong way. Okay, so that's better. When t is 0... when I sub that in, I get 1 minus 0, which is 1 times P0, so 1 of P0 and 0 of P1. Now I'm putting these in here as the whole set of coordinates for the point, but if you want to do the coordinates separately, in the place of P0 you'd put the x coordinate of P0, and in the place of P1 you'd put the x coordinate of P1, and if you want to do the y coordinates you could do that. I think about it as the whole point, because then I only have to remember one thing. Okay, so that's what it is when there's 2 points. If there's P0, P1 and P2, then I'll use P0 and P1 and P2. I'm just going to separate this out. Okay, so what's going to happen is I'm going to use the 1 minus t and the t again, but I'm going to do it like this, 1 minus t squared and t squared at the other end. And in the middle it's going to use 1 minus t and t, and there'll be two of them. And then with 4 points, there'll be a P0 and a P3 and a P1 and a P2. And over this side we're going to have 1 minus t cubed. Over this side I'm going to get t cubed. And these ones, well, this will be 1 minus t squared t, and this one will be 1 minus t squared. So as you can see, the powers of t are going to 1 minus t are going down, and the powers of t are going up, and these will both be 3's. So these coefficients here, we have 1, 1, 1, 2, 1, 1, 3, 3, 1. They come from Pascal's triangles. Pascal's triangle. It does have another name because it was actually discovered earlier in China, I believe, but I can't remember that name. I'm really sorry. So Pascal's triangle starts with a 1, and then on each row it's sort of offset from the row above by a little bit, and then each number you sort of look at the two numbers to the top left above it and the top right above it and add them together. So over here there's nothing to the top left, and to the top right there's a 1. Over here there's a 1 to the top left and there's nothing to the top right, so the sum is 1. Here, 1 plus 1 is 2. Here's a 1 on both ends. 1 plus 2 is 3, 2 plus 1 is 3. So the next one would be 1 plus 3 is 4, 3 plus 3 is 6, 3 plus 1 is 4, 1, and then there's a 1 on the end. So if you had 4 points, or 5 points, you would do this. You'd go like P0, P1, P2, P3, sorry, give myself a bit more space, P4, like that. This one would have a 1 minus t to the 4, this one would have a t to the 4, and then the powers of one will go down, the other one will go up. So this one will be 1 minus t cubed t, this one will be 1 minus t squared, 1 minus t cubed, and then by the time you get there the 1 minus t has gone down to 0 and the t cubed has gone up to t4, and this will be 1, 4, 6, 4, 1. So now you've got the pattern, you can do the Bezier curves. And I probably should do a quick example, right? So, e.g. Bezier curve using 1, 2, 3, 5 and 2, 0. Now you have to do them in order. If they're in a different order you'll get a different curve because, well, it will pass through both of these and will sort of go towards the 3, 5. So different, but if they were in a different order I would have a different starting and ending point. And even if you kept the same ending and starting point and moved the ones in the middle, it would be a different shape. So you need to keep them in the order they're in. So the coordinates of points on the curve are, let's see, we've got 3 points, we've got 1, 2, we've got 3, 5, we've got 2, 0. There'll be 1 minus t squared of these, 2, 1 minus t of these, and t squared of these. And then if I wanted to, I could turn that into individual coordinates, which is what the person marking your exam is probably expecting. So we have, just looking at the x coordinates, I'll just cover up the y's with my texters so that I can see more easily. So 1 minus t squared times 1, 2, 1 minus t times 3, so that would be 6, 1 minus t, and 2 times t squared. And then for my y coordinates, I've got 2 times 1 minus t squared, 2 times 1 minus t times 5, so 10, and 0t squared. So that's what all the points on the curve are, and the t goes from 0 to 1. So let me just check that I've got this right. When t is 0, I get 1 squared, which is 1, which is the correct x-coordinate for the first point. And when t is 0, I get 2 here, which is the correct for the second one. And when t is 1, I should get the other point. When t is 1 here, I've got 0, 0, 2 times 1 squared, which is 2, which is the correct coordinate, x-coordinate for the last point. And when t is 1, I get 0, which is the correct one for the last point there. Okay, so at least my first and last point are correct. And as the t moves from 0 to 1, it will move on this curve between here and here. And it will go towards, but probably not through 3, 5. You could, if you wanted to, at this stage, expand it out even more, expand out all our brackets and get it down to something quite simple, which is probably recommended if you plan to do derivatives and find tangents of and things like that. But I'm not going to do that. But I am going to do the last thing. So, all right, what have we done so far? We've got converting between different representations. Yeah, I'm not even going to attempt to convert this to Cartesian form, it's too complicated. And I've got a specific example, and then I guess we need to know what sorts of things can we do and say about curves. Okay. Well, you can always find the endpoints of a curve if it has endpoints at all. So your Bezier curve, for example, has endpoints, has a beginning and an end. So if t has a domain, I use that word deliberately, that's the correct word for it, because it is technically a function from the set of numbers that t can have into the plane. Then it probably has endpoints. You know, for example, t cubed plus 1 t squared for t between 1 and 5. Well, the beginning is when t is 1. So that would be 1 cubed plus 1 squared, which is 2, 1, and that's the beginning point. So that's starting for the beginning of t. And when t is 5, 5 cubed plus 1, 5 squared. 5 cubed is 125, so 126, 25. That's my end point. Okay, you can always find a beginning and end point. I should be aware that sometimes something's not defined at one of the ends, and so it doesn't have an end. So, I mean, obviously, if t is for all the real numbers, there is no ends. It goes on forever in both directions. So, something like this. I mean, we've got an indication here. I'm not allowed to use 0 because of the round bracket there. But it's not defined when t is 0 anyway. So, t equals 0, it's not defined. Which means no beginning point. But there is an end point. 1 over 3, 5. Okay. Well, the only other thing that we might want to know, well, I mean, there's plenty of things you might want to know, but the things in Maths 1M that we've done that you might want to know about a curve are its tangents. Okay. If you were studying, say, Engineering Maths 2B or Multivariable and Complex Calculus, there are even other things you might want to know about a curve. You might want to know at any particular point what direction the curve is facing. You know how you're tracing tracing the path of a point as it moves, you might want to know, well, what direction is that point moving at any given moment? And that's really about what the tangent is. The tangent is a line that sort of goes in the direction that the point is moving at that spot and passes through that point. And you might want to even differentiate the curve to figure out, well, how fast is the point moving at that spot? Now, when you're not going to really do that in Maths 1M, but it's a really, in my head, a useful way of thinking about how things are working there. So I'm just going to do that. So maybe this goes from t equals 0 to t equals 1. And at different points on the curve, it's going different speeds. So it might be, this might be t equals 0.2, and this might be t equals 0.6, and this might be t equals 0.8. And you'll see that it has to move faster to get from here to here, which is when t is 1. It has to move quite fast here and much faster than it moves here, because they're the same span of t's. It's 0.2 t's from here to here and 0.2 t's from here to here, but it's moving, therefore it must be moving faster here than it is here. And it's going at different speeds. And you might want to know how fast it's going, but that's not what we're actually going to be doing in Maths 1M. You don't talk about how fast it goes. But you can at least figure out what direction it's moving in at any given moment, and that's sort of what the tangent does. So at this point just here, there is a line that sort of shows how far, what direction it's going at this moment. So each point on the line here produces a point on the curve. And if I zoom in on this bit here, it's my magnifying glass. Whoop, let me move my page up. The curve's sort of coming around like this, and the line's meeting it. Okay, this is the point. Okay, so what's happening is that when t moves by a little bit, just here, like that, a little tiny movement of t, that's going to cause this point to move by a little bit, and it's going to move a little bit in the x direction and a little bit in the y direction. And that dy divided by dx is going to be the slope of that line. But the dy is moving when the t moves, and so dy and dt is how quickly the y-coordinate's changing, and the dx and dt is how quickly the x-coordinate's changing. So if you want to know how quickly the slope is changing, well, you'll just divide those two speeds. That's the idea behind finding slopes of tangents. So the slope of the tangent is dy on dt divided by dx on dt. And this here is how quickly the y-coordinate moves, and this how that changes, and this is how quickly the x-coordinate changes or moves. And that's how I think about it. All right. So just a couple of examples to round that off. So for example, let me do this curve, which is only slightly different to one of the other ones I've made up earlier. Okay, so let's find the slope of the curve when t is equal to 2. So t equals 2 is somewhere in the middle of that curve. It's not the beginning point, it's not the end point, it's somewhere in the middle. So I really should know what the point on the curve at that spot is. It's not necessary in order to figure out what the slope of the tangent at that point is, but I just think it's useful. So let's see, point on the curve is 2 squared 2 cubed plus 1, which is 4, 9. Okay, and for any point on the curve, x is t squared and y is t cubed plus 1. So we can do the derivatives of both of those things. So dx on dt is 2t. That's how quickly the x-coordinate changes when t changes. And dy on dt is 3t squared. That's how quickly the y-coordinate changes when t changes. So we can see that as t gets bigger, the x-coordinate continues to change faster and faster. So when t is 1, the dx on dt is 2. When t is 2, the dx on dt is 4. When t is 3, the dx on dt is 6. So the speed at which the x-coordinate is changing is moving faster and faster as t moves along. And the same with the y-coordinate. But the y-coordinate is changing faster than the x-coordinate is changing. Okay? So the slope here is dy on dt on dx on dt, which is 3t squared on 2t, which is 3 on 2t. So again, the slope is getting steeper and steeper as t gets bigger. When t is 2, the slope is 3. When t is 3, the slope is 9 halves, like 4.5. So the slope is getting bigger as t gets bigger. And we actually want to know what the slope is at t equals 2. So at the point where t equals 2, the slope is equal to 3 on 2 times t, which is 3. So basically what that means is that my curve here at the point 4, 9, the tangent here has a slope of 3. So for every one across it goes up 3. So it's like that. That's my tangent. My curve, I think, is on this side because the y is increasing faster than the x is increasing. There we go. Now I could, if I wanted to, calculate the equation of that tangent. I didn't ask, this question didn't ask me to, so in an exam I wouldn't, but just for completeness' sake so that you can see how it's done. So, equation of tangent is y equals mx plus c for some m and c. Okay. Now we know what m is. M is the slope, and we've just figured that out. So the slope is 3, so y equals 3x plus c, and it passes through the point 4, 9. So when I sub that into the equation, it'll work because that point is on that line. So 9 is 3 times 4 plus c. So 9 is 12 plus c. So to subtract 12 from both sides, 9 minus 12 is minus 3 equals c. So the equation of the tangent is y equals 3x minus 3. Sweet. Now there are a couple of specific tangents that you might want to know. Sometimes your tangent to your curve will be horizontal. I don't know why you'd want to know that, but you might. It will be horizontal, and sometimes it'll be vertical. And the vertical tangent has no slope. You know, it doesn't have any way of calculating slope because its slope is infinite. But you can still figure out where it is because the vertical tangents happen when dx on dt is 0. Okay, and I can imagine that that's right. So if you've got your point somewhere and your tangent's vertical, that means that when your pencil passes that point, it's pointing directly vertical at that spot. So at that spot, the change in the x-coordinate is 0. The x-coordinate is not changing because you're going directly up. So which is why dx on dt is 0. And the horizontal tangent happen when dy on dt is 0. Because again, if the point as it passes that spot, if your pencil point as it passes that spot is going directly horizontal, then the y-coordinate's not changing, and so dy on dt is 0. And you could do some examples of that. I'm sure there are some in the lecture notes, but I've sort of run out of time. So I'm going to stop there. Thank you very much for listening. Don't forget there's other revision seminars on other things. And if it's still 2016 and you're watching this, you can request topics for next week's seminar. Thanks.